Welcome to this maths video on numerical integration. To start with, let's take a look at the trapezium rule. Now, to find an approximate area under a curve, we can split the area into multiple trapeziums, and then we simply add the areas of these trapeziums together. The area of each trapezium is given as the following formula. So this is A equals h over 2 times yn plus y of n plus 1. Okay, and in that case the area is then represented by the integral here from a to b of y dx. Okay, and this is approximated by the following formula here. So the integral from a to b of y dx is approximately h over 2 times y naught plus our last term, so that's yn, so that's y naught plus yn, and then we do two lots of everything else. So in that case that's going to be two lots of y1 plus y2 plus all the way up then to yn minus 1. Okay, so that's everything else other than the first term and the last term. Okay, and that's how we approximate the area then. Now n here is the number of intervals, so n is the number of intervals. So n is a number of intervals. H is the width of each interval, and the formula for h is b minus a over n. So h is the width of each interval, and h is represented by the following formula of b minus a divided by n. And y0, y1 up to yn are the heights of the sides of the trapeziums, and these are obtained by substituting the appropriate x values into the equation of the curve. And what we can see here then is this looks something like this here. Okay, where y equals f of x, and we can see each trapezium as we go along then. Okay, so that gives us everything we need there for the trapezium rule. Moving on now to take a look at underestimates and overestimates. Now naturally, when using an approximation method, you will either get an underestimate or an overestimate of the true value of the area. And the shape of the curve dictates whether your approximation will be an underestimate or an overestimate. If the slanted side of the trapeziums are above the curve, then the approximation for the area will be an overestimate. And this is the case for convex curves, and we can see it looks something like this. So if the slanted side is above the curve here, which we can see by this red dotted line, that means this will be an overestimate. Okay, and remember this is for convex curves, so convex curves. And if the slanted side of the trapezium is below the curve, then the approximation for the area will be an underestimate. And this is the case for concave curves. And again, we can see this here with this red line being underneath the curve. Okay, and again, this is the case for concave curves there. And like we said, this is an underestimate. So this is an underestimate. And this is an overestimate. Okay, so that gives us everything we need there for underestimates and overestimates. Moving on now to take a look at upper and lower bounds. Now the trapezium rule will give an approximation between two bounds for the area under a curve. These upper and lower bounds are found by considering rectangular strips that lie above and below the curve respectively. One bound is found by summing the areas of the rectangles which meet f of x with their left hand corner using the following formula. And before we give the formula here, let's just see what this looks like. So as we can see here, this is the left hand corner. Okay, and the formula here is the integral from a to b of f of x with respect to x, and this is approximately h times y0 plus y1 plus y2, and this is all the way up then to yn minus 1. Okay, so yn minus 1. Now the second bound is found by summing the areas of the rectangles which meet f of x with their right hand corner using the following formula. And again, before we give the formula here, let's just see what this looks like. And again, we obtain that something that looks like this. And again, we can see here it's the right hand corner of each rectangle. And the formula here, again, looks very similar. This is the integral from a to b of f of x with respect to x. And this is approximately h times y1 plus y2 plus y3 all the way up then to yn. Okay. Now, if you are calculating the bounds of a curve with a turning point, you will need to use the formula for one bound on one side of the turning point and the formula for the other bound on the other side. Okay, so make sure to take note of that. So that gives us everything we need there for upper and lower bounds. And finally, let's take a look then at when integration is the limit of the sum of rectangles. So using the limit of the sum of rectangles to find a definite integral uses a similar idea to differentiating from first principles. Differentiating from first principles involves finding the gradient of a straight line between 2 points on a curve of an interval. And as the interval, delta x, gets smaller and smaller, so as delta x tends to 0, the gradient of this straight line gets closer to the gradient of the curve at these points. And we can use the area of rectangles to find the definite integral between 2 points. So the area of each rectangle is simply given as the height times the width, which we write here as f of x times delta x. Okay, so times delta x. So the approximate area under the curve is the sum of the areas of the rectangles, which is written as following. So that's going to be the sum here from x equals a plus delta x up to b here. That's our upper limit. And this is f of x delta x. Okay. And like with differentiation, the smaller the intervals, the more accurate the approximation. So therefore, as delta x tends to 0, the sum of the area of the rectangles approaches the definite integral. And we can write that as the following. So this is the limit as delta x tends to 0. The summation here, again, where x is equal to a plus delta x up to b is our upper limit of f of x delta x, and this is equal then to the integral from a to b of f of x with respect to x. Okay, so that gives us everything we need there for integration is the limit of the sum of rectangles, and that concludes this Maths Made Easy video on numerical integration.